Assalamualaikum warahmatullahi wabarakatuh. Dear all participants of the second annual Engineering and Vocational Education Conference 2020, allow us to present our paper entitled The Role of Resources in Enhancing the Fresh Properties, Density and Compressive Strength of Fly Ash-based Self-Convecting Geopolymer Concrete. The author of this paper are Denny Ardiantoro, second, Ernawati Sri Sunarsih, and third, Taufik Lilo Adi Sujipto. We are from the Building Engineering of Education Department, Faculty of Teacher Training and Education, 11 Maret University, Surakarta, Central Java, Indonesia. I, Denny Ardiantoro, as the presenter for this presentation. First section's introduction. The production of Portland cement as a concrete material is one of the causes of carbon dioxide emissions in the world. Another problem is the use of resource waste, which is not used properly. Another problem in the construction work is concrete compaction. The vibrating compaction of concrete causes environmental noise and increases work costs. To protect the environment from damage due to excessive cement production, resource waste, and concrete freebasing compaction, an alternative concrete is needed. Self-convecting geopolymer concrete is a solution for environmentally friendly concrete with low carbon dioxide emissions, self-convecting ability, and the use of resource ash waste as raw material. This research aimed to investigate the role of resource ash in enhancing the fresh properties, density, and compressive strength of fly ash-based self-convecting geopolymer concrete. Second section's theoretical foundation. Self-convecting geopolymer concrete is a combination of geopolymer concrete and self-convecting concrete technology. Geopolymer concrete is a concrete without Portland cement as the painter's material. Geopolymer concrete comes from the chemical reaction of silica and alumina oxides with alkaline polysilicate to form a polymer with COL bonds. Self-convecting concrete is concrete that has ability to flow and compact itself without requiring convection or vibration. Materials. Material from ACGC was silica and alumina molecules such as fly ash and resource ash or RHA, alkaline solutions such as sodium hydroxides and sodium silicate, fine aggregates and coarse aggregate, then superplasticizer. The specification of fly ash and RHA can be seen in the following slides. The third section, research methodology. The methodology in the study can be seen in the following flowcharts. First, material preparation and testing. Fine aggregate supplied by PT Panjaibeton Karanganyar, Central Java. The results of fine aggregate testing can be seen in the following table. The coarse aggregate supplied by PT Panjaibeton Karanganyar, Central Java. The results of coarse aggregate testing can be seen in the following table. Second, mixed design. The HCGC mixed design used the AEVEC self-convecting concrete standard with a compressive strength of 30 MPa quality plain concrete. Ratio of sodium silicate and sodium hydroxide was 1.0. Sodium hydroxide molarity was 14 m. The superplasticizer used Consol SS 74N from PT Indonesian Construction Chemicals with 1% dosage. The water binder ratio was used of 0.3. Material requirement from ACGC can be seen in the table. Third, fresh properties, testing, and concrete curing. The first properties of ACGC test in the study were slam flow. The diameter assessed by the flow of concrete for normal application of AEVEC standard is 65 to 75 cm. In the study, the curing of ACGC used ambient temperature for 28 days. The fourth sections, result and discussion. The slam flow test results. The results of ACGC slam flow testing and graph of the effect of RHA substitution on slam flow of ACGC can be seen in the following slides. Based on ACGC slam flow data processed using SPSS program, it was found that the addition of RHA had a significant effect on the ACGC slam flow. Obtained from SPSS program, the maximum percentage of addition of RHA to a safe AEVEC slam flow standard was 7.16%. The slam flow value of ACGC with a percentage of 0 and 5% fulfilled the AEVEC slam flow standard. Meanwhile, the slam flow value of ACGC concrete with 10 and 15% RHA substitution variations were not fulfilled for the AEVEC slam flow standards. Based on graph, it can be concluded that the variation of AEVEC substitution reduced the slump flow value of ACGC. Based on previous research, the decrease in the slump flow value that occurs is due to the high reactive silica content in RHA accelerates the geopolymerization rate of ACGC mixtures so that setting time of the mortar materials occurs faster. Density test results. The results of ACGC density testing and graph of the effect of RHA substitution on density of ACGC can be seen in the following slide. Based on data from the ACGC density test results processed using SPSS program, it was found that the addition of RHA was not significantly affected the density of ACGC. The specific gravity between RHA and fly ash does not differ much, so that it does not significantly affect the density of ACGC concrete. ACGC concrete is included in the classification of normal concrete with density of 2122.391 to 2133.939 kg per meter cubic. Compressive strength test results. Results of ACGC compressive strength testing and graph of the AEVEC of RHA substitution and compressive strength of ACGC can be seen in the following slide. Based on the results of the ACGC compressive strength test data processed using SPSS program, the results showed that the addition of RHA had a significant effect on the compressive strength of ACGC obtained from SPSS program. The maximum compressive strength of ACGC was 11.476 MPa and the percentage of RHA substitution 8.65%. Based on the graph of the compressive strength test results, substitution of RHA by 5 and 8.65% increased the compressive strength of ACGC. Based on previous research, the increase in the compressive strength of ACGC occurs because the addition of RHA increased the CL ratio, so that the polymer bonds formed were stronger. The optimum compressive strength of ACGC was obtained at the presence of RHA substitution of 8.65%, and after that there was a trend of decreasing compressive strength on the presence of RHA substitution 10 and 15%. Based on previous research, this is due to the high silica content in RHA, which is not directly proportional to its low aluminum content, so that when the COL bond polymerization reaction occurs, the excess silica content in the RHA does not react because of the lack of alumina compounds. The last sections, conclusion. First, the substitution of RHA significantly decreased the sum flow value of ACGC. Second, the substitution of RHA didn't have a significant effect on density of ACGC. Third, substitution of RHA significantly increased the compressive strength of ACGC. In the presence of RHA substitution more than 8.65%, there was a decreasing trend in compressive strength. That's all the presentation of our paper. Thank you. Assalamualaikum warahmatullahi wabarakatuh.